Hello, this is Kan-Lin speaking. In this section, we're going to talking about the heating value of various fuel. The heat from the heating value actually means the chemical energy, how much possessed and can be released through the electrochemical reaction of the fuel cell. From there, we'll be able to estimate the energy conversion efficiency and then the energy density of the fuel and so on, or even the fuel cell voltage. Let's see, for the heating value actually can be divided into the high heating value and the low heating value, LHV or HHV. The high heating value, just we mentioned before, is a combustion of hydrogen with the excess of the oxygen. So make sure all the hydrogen in a calorimetric bomb was completely consumed. And then product is liquid water. Then this we call the high heating value. And the low heating value is when the product is a gas phase water. Over here, the calorimetric bomb actually might be like a stainless steel canister, and then the hydrogen and the excess oxygen will filled inside the canister, stainless steel, and then the spark plug will ignite and then cause the combustion. The combustion heat release will be diffused outside the canister, and the whole stainless steel canister is actually soaked inside a water bath. So the increase of water bath, you can calculate how much heat released from the hydrogen combustion. Actually, there's two different type of heat release beside the high heating value and low heating value. One is if a canister is a fixed volume, that means airtight. So the combustion is taking place in a constant volume. Then this will be a release the constant volume heat. The other possibility is if you had a piston. So we'll make sure the pressure in the combustion chamber is keep constant. In that case, it's a constant heat combustion will be different. So this hydrogen and oxygen had their own original chemical energy. We assume is at a higher level. So when it's burned, combust, and then release the water vapor, then this energy difference we call the low heating value. So this hydrogen's low heating value per mole of hydrogen, how much energy will be released if the end product is a steam or water vapor. But if it is a liquid water, then we call the value is a high heating value. And the difference is the heat of evaporation or heat of condensation, depends on how the initial state and the final stage. So if your initial stage is a liquid water, then the final stage is a vapor or the steam, then we call the heat of evaporation. If the initial stage is a water vapor and the final stage is a liquid water, then we call the heat of condensation. HV is the latent heat between the gas phase and the liquid phase. The high heating value, the difference between these two, as mentioned, is equal to the evaporation of water, the latent heat of the water. This one we can write as a HHV equal to LHV plus 45, the difference. That means the difference between high heating value and low heating value of hydrogen. So in general, we can write down as this equation: the high heating value equal to low heating value plus the heat of evaporation of water multiplied by how much water mole of water will be released divided by per mole or of the fuel. So for the chemical, if it contains more water, then the difference between high heating value and low heating value is greater. depends on how much the water will release. In this case, we give an example. For the carbon, there's no hydrogen in the carbon material. For instance, ideal case, or burner will be generate only the carbon dioxide. So there's no water inside, so the N equal to 0. Then we got a high heating value is equal to low heating value. For the methane, they will generate, each mole of methane will generate 2 mole of the water. So each mole of methane will generate 2 mole of water. So this will equal to 2 multiplied by this. So in this case, the high heating value of methane is much greater than the low heating value of methane. This table gives you a different kind of fuel, and the high heating value and low heating value, and the difference between the high heating value and the low heating value. All this more or less like diesel or propane, and this kind of like a pure compound, so we can estimate the different heating value. But for the coal, even the coal, there's different kind of coal, and then their composition actually depends on where it's product. So this one just give an approximate value of this. Again, the value can be calculated if you know the exact composition. Actually, you can calculate the difference between high heating value or low heating value. So the next we can talk about the energy conversion efficiency, because the purpose for the fuel cell is try to generate electricity. So even for this cell, we can see from the chemical energy of the fuel will generate electricity and heat. It will make an energy balance, but actually what we more interest is on the electricity rather than the waste heat. Even the waste heat can be recycled and reused. So we are more or less focused on the conversion of chemical energy into the electricity. So there's a conversion efficiency from the chemical energy to the electricity. So for a given chemical energy, we are more key on how much electricity can be produced. That's the for the fuel cell point of view. We had to because the electricity is major what it want to do. So in this case, the efficiency is can be said is how much chemical energy you had, and how much electricity will be generated through the electrochemical reaction or the fuel cell. And this is the epsilon I is called intrinsic efficiency. It's not depends on the design of the fuel cell or peripheral or kind of other things, but only based on from thermodynamics. Just calculate from the material itself, chemical itself, how much predict the most ideal case, how much the efficiency can be produced by this kind of fuel. So in this case, the epsilon I, the intrinsic efficiency, equal to delta G divided by delta H. This is the entropy of change, and this is a free energy, change of free energy. The relationship between delta G and delta H can be given by this equation. We still give hydrogen as an example. Then the delta G equal to delta H minus T delta S from the thermodynamic second rule. And then the delta G is a free energy, change of Gibbs free energy. And delta S is a change of entropy here. And actually, they are the same for this chemical reaction. You can check on the table. You can find the entropy for each species, or the heat of formation and the enthalpy for each species, or even the free energy for each species. Depends on how you find you also can calculate the change of the entropy, and free energy. They should have this relationship. Following, we give an example. I use as hydrogen as the example, hydrogen fuel cell. And over here, I give the enthalpy for each species and the entropy for each species. Be noticed, this unit is different. slight different. Let's divide by Kelvin here. So you can add all this, the enthalpy here, entropy here. You multiply by the same equation. You end with the delta H and the delta S, how much. Then substitute into that equation. You can get the delta G, how much is the free energy change for this electrochemical reaction. And if you know the delta G and you know the delta H from here, you'll be able to calculate the energy conversion efficiency, the intrinsic efficiency of the fuel cell reaction. So this one we talk about the heating value of hydrogen. Next, we're going to talk about the fuel, the energy density of fuel.